Welcome to my second talk. This is my last talk for this conference, and I hope that I can enjoy some entire conference and have fun afterwards, really. And this talk is a bit more complicated than the first one, and it is not about hashcat exactly, it is more about the algorithms that are used to hash passwords, and it is.
Half your slides are not showing.
Sorry?
Yeah, I think we have to change the resolution. That was possibly going out. Change to just go back to only that.
Can you try the PDF?
Yeah, so we can see the entire.
Absolutely, thank you. This is more a talk about the hash algorithms behind the passwords and how to optimize the cracking of them. This is not dark art, and I don't like that word. What I'm trying to show you here now is that this is not so hard as you might think it is. I will not use any academic type hieroglyphs because I, for myself, I'm not academic type, and for me it is always very hard to understand the papers, academic papers, when they show how an algorithm can get attacked. And this presentation is a bit more how it looks from the programmer side. So you will see a bit of C source code, not too much. I will explain a bit about that. And in the first section, I will explain a bit about general techniques that can be used to attack algorithms, the basic ones, and this hopefully focus your eye as an attacker a bit. And then in the second section, I will explain how you can, or how these general techniques has been used to attack MD5 and MD4 SHA war example. So you have 5 general techniques that you can use. I will start with one note about how this is known. All of this stuff is known. Some is more, some is not. And it is all used in also hashcat line. So if you are coding a cracker and you want to use these techniques, you can take a look at also a hashcat line, which speed you can get at also a hashcat line, and so you can compare the drawn cracker. And is this your optimal code? I think also a hashcat line is pretty good in speed. So yeah, you can compare it that way. So the computer's view on passwords is very simple. The word password, for example, takes two 32-bit integers from computer's view, but hashing algorithms work block-wise. So typically on 32-bit algorithms, you have a 512-bit block, and inside that block you have placed the password. It starts from 0, so as you can see here, you use only two 32-bit integers of the possible 16 ones. In this example, you can see that only the first two are used and the other ones are not. So we have that W array. The W array is how that 512-bit buffer is called, and 0, so it is 0-based. So pass in the 0 and bird in the 1, but the rest is 0. And if you take a look at one of the MD4 step functions, you can see that I will do it in another slide, but this is a standard MD4 function. And this function is called 16 times before it changes the function. So if x is 0, x is one of the 16 elements from the W array. If x is 0, and we know that, if we know that the password has only the length 8, we do not need to use this addition, that plus x, because something plus 0 is the same value as it was, so we can completely optimize this out. And by doing this, we can optimize MD5 by 36 instructions and 48 for MD5. This works on all algorithms I have seen so far, because they all use the password in a fixed size buffer, and so they have to access every element of that buffer at least once. And if it is 0, mostly no function that is used will change the value afterwards. Another basic techniques is the initial step optimization. This is MD5, the first steps, and MD4. Yeah. Okay, so yeah, the only difference between MD4 and MD5 is that you have the AC added to and the x and the function to a afterwards. So the problem is that when W0 is 0, all other data is known, and we can replace the original MD5 step macro with a constant value, because the constant value A is known, B, C, D. We know that W0 value, we do not know W0 value, so we have to add it afterwards. But all the rest of the function and the AC, the constant, is known, which results in this constant. We only need to add W0. And by doing this, we have in MD4 and MD5 instructions saved. The next step can be optimized like this, but the function or the efficiency of that optimization is less, because we have to add B, C, and D function, which change in the first step. Then the last step can also be optimized. The thing is, passwords do not exceed a specific length normally. And if they do not exceed the length 55 for 30-bit 2 algorithms, the method Delgard construct does not apply, and we stay in the first transformation. Since we know A, B, C, D, since it is the first transformation, because they are constants, we can subtract it from our hash we want to crack. And when we subtract it, we know the value of A at the last position. So this is our example hash we want to crack. This is A, first A of it. You can see that here. We know the suffix constant of MD5 at that stage. We subtract it, so we want to search for that value. And after this position, because this is the last position where A has changed. And this looks like this. So we return, and we do not need to calculate this block. So for MD4, we saved 3 steps. For SHA1 we can step five, we can say 5 steps, but this needs an additional calculation, but I will show it after that how this will work. Then the pre-computing, depends a lot on the possible values that we want to pre-compute and how much RAM we have, fast memory we have, that we can access on the possible values from as a key. So, for example, we want that SHA-256 algorithm. You can see here, this is one step of SHA-256. And we do not change the first 4 characters in our password candidate generator. Then, so if it stays constant, the first element of that buffer, and you know that A to H are constants again, K0 is a constant, and W0 does not change. We can completely pre-compute that step completely. So we do not need it in our outer loop. So we can start from the second step. And the last general techniques is the partial reversing. This is really nice and a bit more complicated to understand. But one important thing is that that statement that hash algorithms are one-way functions is true and it's not. We can reverse an hash, but not in a way you might think we cannot reverse to the password, but we can reverse to the constants. So if we know the password correctly, we can reverse from a hash back to the constant. And if the constant matches, we know we have used correct buffer as password. So for example, again in MD5, if we hold the first 4 characters constant, the rest constant and the first four not, as you can see here in that example. This is an important part, because we can now, in the outer loop, partial reverse MD5, and in case we need to change the W0, we need to recalculate from the outer loop. And inside the inner loop, we can go straightforward as usually, and once we hit the step from 1.1, we can compare these I call it intermediate digest, and we can compare it. If it does not match, we can skip the rest 16 or 17 or 18 or whatever your implementation is steps and save them. So these are the general techniques, and now I show you some of the known algorithms and how these techniques can be used in these algorithms. For example, MD4, which is used in a lot of algorithms, can be used with nearly all of these optimizations. And this is one of the reasons why you can calculate NTLM hashes and MD4 that fast, like the 15 billion hashes per second, I think, for almost single settlement set. So it's also a very good example to show how to do partial reversing, and I will show you how to do this up to step 30 from 48. So this is the original step from MD4, and you can see the reverse version, the inverted version, It's doing exactly the same, but it's not tracked as. So this looks very, when I saw it the first time, I thought this cannot work, but it does, because it will underflow, and what algorithms do is, once they hit the 32-bit mark of an integer, they overflow, they want to overflow, and so we want to underflow, and it works. So the first step we need to do is we need to call the inverted functions from 48, from before, back to 34. And when we do this, we have the last value of d. And then, at this point, we cannot reverse any longer, because this is the point where W0 changes, and we need to hold W0 constant. So each time we have to change W0, we have to do again all the inverted functions. So we have the last intermediate value of d. So we can compare at that position when d was changed the last time. So the mean in the middle comparison is after step 30. In the inner loop, we just compare compute and before forward, and at step 30, like with early exit, you return the bit of no match. So 33 speed, percent speed increase is not bad. So 95 is, yeah, I don't know, nearly everywhere used, especially in web-based applications. And all the techniques work here as well. It looks a bit different. So it's just minus b at the end, and before does not have that step. And it works exactly the same way as before. And we only need to calculate 46 steps. SHA1, same, it's used nearly everywhere. And I think, no, there's another optimization possible that I have presented at PasswordsCon, which does not match the generic attacks I showed before. But if you want to learn about it, here's the URL, and you can take a look at it. But there's another optimization possible with SHA1 for value access. So I said SHA equals the same as NV4 and NV5, but yeah, you see the constant at this point. So this is the constant from the initial A, B, C, D, E constant. So at the end, like in a typical implementation, we have set E here the last time. So usually you would say you have to check E after step 77, but if you take a close look at it, it's this one. There's a data loss because it's just a rotation, and since it's a rotation, you can do the opposite again. So if you something rotate to 30, you can rotate it by, to the right by 30, and you result in the original value. So in that case, we can do our value exit at step 75 instead of 77. So this gives another 4 steps of AE, and it works together with the XOR implementation I showed at PasswordsCon. And TLM, also an early exit, but a very, very efficient early exit. Here's an example how method and TLM key1 hashes generated. So the hash value of or call it an T hash of hashcat is this one. So the first step you have to do is break it into the 356-bit pads, and you can see, since this is a 128-bit hash, you have to pad it at this point. So I just pad it with zeros, then some aligning stuff here. Still, the MD4 output, which is only 128 bits, uses that 16 bits, the last ones. So then the challenge key is used to DS encrypt the free 56-bit keys, and yeah, the key of the DS buffer is limited to that 16 bits. So when we are inside our inner loop and we do the anti-hash, and we have brute forced the first 16 bits of DES, which can be done in less than a second, and we can compare the last 16 bits of the NTLN. And if they match, we do not need to calculate the DES stuff. And the DES stuff is very slow on CPU, but the MD4 is very fast. So we can say the entire DES calculation, in other words, that makes the net NTLM V1 hash exactly as fast as NTLM. So this is one of the most massive gain of performance I've ever seen. So you get 5 to 10 times faster calculations. Whirlpool, not so much used, or newer algorithm, but since it is used in TrueCrypt, for me it's an important hash function. Since TrueCrypt is an important encryption thing, so Whirlpool, yeah, with Whirlpool we can pre-compute 50% of the entire calculation by pre-computing the K array. And if you want to take a look how this works, here's an URL. It's already up. You can try it. It will pre-compute the boxes for you. But there's more. So once you have pre-computed K, you can use these pre-computed values and reverse your hash again. So it's again partial reversion possible. So you can, the PC is the pre-computed K. Yeah, there's still more room for optimization, but at this point we have reduced it by more than 50%. And this is the funny thing, it works with HMAC, and since it works with HMAC, it works inside PBKDF2, and since it works with PBKDF2, it works with True. Yeah, this is Oracle Old. It's good, they changed it. So the thing is, it uses DES. It just uses DES with static IV and a static key to encrypt the password. So, and because it uses a static IV and a static key, we can pre-compute by 100% the sub key that is required to cipher a bit of data, in that case the password. So we have already saved the entire sub key files. HMAC. Okay, HMAC is very important. You can see the stuff. WPA, I mean, used everywhere. TrueCrypt, again, looks. HMAC itself is not a hashing algorithm. It's a construction combined with hash function, and it is very good in defeating the zero-based optimization. That is because it is filling the buffer, the 512-bit buffer, with static values. And since these values are no longer zero, we cannot use zero-based optimizations. And there's another important thing about this. It is using exactly that length of static 3636 and 5Cs as the transformation for one block is doing. So in that case, 512 bits. So we can pre-compute that part. This was this part and this part. So we can pre-compute this edge and this. So we can say total and a total of 50%. And this works with WPA. So, custom schemes, I wanted to add some more to this, but I have no time.
Yeah, no more time.
No more time?
You have 30 minutes more, so go on.
No, I mean, and that's
Okay.
fine. So, first one is the IPv2. IPv2 is using MD5, and in a very strange way, they are hashing with MD5, and the result is the ASCII hex representation, and that one is hashed again. So the sort is fixed, and since the sort is fixed, we can pre-compute that part for the entire thing. So instead of doing 3 MD5 calls, we just need 2. So we have more than 30%. And one password, okay, that's a bit more complicated to explain. One password uses, or used, they changed it, right?
It's changing, it's in transition.
Okay.
So most of the one-level data out there is subject to that.
Okay. I will try to explain. So PBKDF2 has an option. You can say you want to configure how much bits of output to produce. So in this case, we have SHA1. SHA1 produces only 160 bits. But for one password, we need 256 bits. So we can configure PBKDF2 to produce only 256, and it will truncate the rest of it. So since it can only produce 160 or 320. So this is one thing. So to do this, it needs to calculate SHA1 twice for the first 160 bits and then again for the second 460 bits. So one password uses AES in CBC mode. So CBC mode means we only need we need to know the previous value, which is used as an IV, is used as the IV. So we already know 1040 bytes from the keychain, from the one password keychain, and we only need the last 32 bits to compare. So if it matches the padding from the AES, we know we have used the right key. So all we need is to calculate 128 bits instead of 265 bits because we know the ID. It's presented us in the keychain, and so we can say 50% of the calculation at all diluted that problem, and we can say 50% of the calculation because of the HMAX problem I described before. So in total we have increase of 400%. So, and I'm sorry I'm a bit too fast. Yeah, maybe we can do a bit of pause afterwards. That's it.